Hello, everyone. So my name is Matheus, and I'm here to present the CloudWalk Paper Club session this week. So in this week, I'm going to present the UNet paper, UNet Convolutional Networks for Biomedical Image Segmentation. And I also talk a bit the paper that I originally chose, but is actually very short, just 4 pages. That is the usage of UNet for pre-processing document images. But then I think I will go into first the UNet paper, and then this one I will show as a case example. And they also have some interesting ideas that I think can generate some discussion for us, right? So basically here you have the UNet. So the name of the paper goes like, what is the main thing of the paper? It's an architecture that was developed by these guys from the University of Freiburg, that basically they go into medical image segmentation, but we can I'm going to show also some other examples that they have. So it's not only for biomedical imagery, also this other paper is for document analysis, but also they have lots of uses for, satellite imagery or object detection and stuff like that. So basically here on the abstract, they go into like this architecture, right, the UNet, and they say here like, oh, this architecture consists of a contracting path to capture context and a symmetric expanding path that enables precise localization, right? So what does that mean, right? So I'm going to explain later on the paper, right, as they explain this stuff. And as like this paper is from 2015, so it's kind of an older paper, but also at the time of when they published the paper, they won this ISP BI cell tracking challenge. So, and also achieved some state of the art in other challenges for biomedical image segmentation, right? Okay, so basically in the introduction, they talk about, like the breakthrough, so here we have AlexNet and stuff, like how you are able to win the ImageNet challenge. So ImageNet is a huge data set that you have 1,000 classes, and then you want to identify which class each image belongs to, right? And here they say, right, the typical use of a convolutional neural network is on classification tasks, where the output of an image is a single class label. So what does that mean, right? So what does that mean is that you have, an image as an input, and then you do some operations on the image, some convolution operations. So you apply some filters, you do some, you pass the filters to do some feature extraction, and then you do some flattening of the feature maps. And then at the end, you have an input of an image, and the output, let's say that you want to predict like between 3 classes, like if an image is a dog, a cat, or a mouse. The output will be an array of 3 values, and then you have like, and each of the 3 values will be like the percentage that this image is associated to this class. So maybe you have like an image, and then the output's like, oh, the array for dog is 90%, the array for cat is 10%, and the array for mouse is 0%, right? So basically that's the idea of what they say here is the most typical use of a convolutional neural network. But then they go here like, however, in many visual tasks, especially for biomedical image processing, the desired output should include localization. It is a class label is supposed to be assigned to each pixel. So what does that mean, right? So basically, this means is we don't want like to classify an image, but we want to segment an image, right? So which pixels of the image is this class, which pixels are background, etc. So here, like, for instance, if you go to Google and then you search like UNet segmentation, you can have some examples here, right? So you can see here like, oh, you have an image, an input image, but then you hear like, oh, these pixels here in purple are road, and these pixels, of course, this is just for us to visualize, right? But bear with me here. So, in red, you can see there are people, and then in blue, it's the cars, right? So it's able to understand like what is car in the image, what is road, what is people, what is light. So pay attention and stuff like that. So this is really important, right? And then like you can see the context here, like how could we make this problem like a classification problem? It's not a classification problem, right? Because you want to understand the image. It's more like detecting what is in the image. And then here, just to go a bit down here to show other examples, we have here, this is an example of the paper itself. So we have here an image that's really low contrast, but you have some cells here. And then you want to identify, oh, what is cell and what is not cell. So here you see like different colors, like it's able to identify the cells in the picture. And I think another, interesting example is down here. Let's see, okay, here. And this one is like for ArcGIS, so it's like geospatial data, right? So here you have some satellite imagery, and then in the end, you apply a unit, and then you're able to identify, oh, this is a lake, or this is, oh, you have here in black the roads, the pixels that represent the roads, and here in red, you have the pixels that represent the houses, right? So basically, that's the idea of what the guys mean here by you have a class label assigned to each pixel, right? So you have an image as input, and then you have an image as the output with some masking of the labels. Okay. So basically, here is the photo of the unit, right? So have some architecture here, we have some feature maps, then have a downsampling path and upsampling path. I'll go into more detail later. But basically here, they say here, like in this paper, we build a more elegant architecture that is called fully convolutional neural network, right? So basically, it's here, right? So here's the, can you guys see? Or should I zoom in more? It's okay?
It's okay for me.
Okay. So basically you have here like images. So you have here in the arrows are the operations. So here in blue you have the convolutional operation, like, so you have a convolution 3x3. So at the start you do this, right? So you have 64 feature maps. And then later they apply this downsampling operation here, right? Which is the max pooling layer, right? So basically you have an image here like it's 568 by 568, and then you have this size of image. So now it's 284 square, right? 284 by 284. And then they apply this operation successfully, the downsampling successfully, which is kind of similar to, like I said, the traditional neural networks, right? Like I said, like for classification, right? So you do like, you start always with, a very large image, and then you apply some max pooling layers, which is good, I think, to get like some summarized, you compress the data, so you try to get what is more important, but also, you save computational power, right? Because this is the kind of paper to 2015 that the computational stuff were still really important, right? We were able to fit on GPU in memory, etc. So basically, what would be a classic neural network for classification? So we have a very similar path here. At the start, this contracting path that they do the max pooling operations, but then, for instance, in the end, oh my God. Okay. So in the end here, you don't do that. So let's say you apply, let's say a large filter, you apply a flattened operation on the feature map. So now we have, instead of having the filters, we have just an like, instead of having, like some images, like a feature maps, you have some array of numbers, right? So it's really flat. And then with that, you can later apply some, I don't know how to use this, but you have some fully connected layers, right? And then finally at the end, you have like some output. And like I said, like you can have like an array of, I don't know, size 3, the image, and say like, oh, the probability of dog is this, the probability of being cat is this, the probability of being a mouse is this. So it's a mouse at the end, right? So basically you start convolutional layers to extract some features, but then in the end you do some flattening of that and do some traditional fully connected layers to get, from the extracted features, how you get the classification part, right? Okay, so let me just delete this, everything here. But basically, like the problem said, like we want a image at the end, right? So basically we use this contracting path here. It's not this that I want the thing here. Okay. So this part here is the contracting path here, and like I said, like we're applying these max pooling operations and then the feature maps here. So basically here we are able to get like we're also we are reducing the resolution of the image, so we are also trying to summarize what is important in the image, right? So here is what the guy said of the abstract, that we have context. So here we are getting the context of the image. But, as we have, the images and we are reducing the resolution at each step, we are also losing resolution of where the thing is, right? So, like, you may have an image here, then you have a very small thing here, but then you have future layers, like, you have some high activation here, right? But then, like, if you don't do anything, like if you just increase the size of the image, like, maybe there's something here, right? So we kind of lose. To learn the features, we need to do this, but also we need to do something to be able to identify correctly, like where this point is, right? Okay, let me delete that. Yeah. So for this, they have this other path here, right? So here, which is the path where in the abstract the authors talk about localization. So basically here we are upsampling the image, and with this we are able to get an image that is not the same resolution but a very similar sized resolution of the image. And then you are able to get like an image that we understand what is important in the image with this context path, but also we understand where precisely it is with these upsampling features, right? So let's see. So basically, the architecture is this, right? So you have a path that you do this downsampling stuff, and then you upsampling stuff. So you start, reduce the size of your feature maps, right? To really here, like you have an image that started at 572 by 572, and in the end you have an image that's 30 by 30, so it's really small. And then at the end here you have one that's almost 400 by 400. Okay, so they do this, and what is important of the unit also, right? They have these operations here, right? That they do, basically they just do a concat of the feature maps from previous layers. So this is like, it's called skip connections, and something that I was really, it was a breakthrough paper that is called HasNet, that they do this. So they have some blocks and they, they just directly connect previous layers to future layers, like the layers, not just the one next, but they connect to the other layers as well. And this has shown to improve results on image classification tasks. And here, I think it's also kind of important because it also shows how, you have some context-rich information here at the end of these smaller layers, but in the end, also you are able to concat, like, so every time you do a upsampling operation, you're upsampling the feature maps that we have that are context rich, but you also have, the equivalent, not so rich in context, but rich in the localization aspect, right? Because they have higher resolution, right? So you're kind of combining the high level information that you're able to get, but also like, maybe where it should be, right? So it's not too bad, right? I think, what else can I talk here? So why this is done, right? So why downsample? Why you just apply all filters of the same size, right? So basically, like I said, you have like the computational aspect of it, because it'd be too huge computational power, but also there's some aspects of it that I think are interesting, right? Because like we like all the layers are applying a 3x3 convolutional layer. So let's think that you have like I don't know, something like this thing here. So this is too thick. Okay, so you have here, this is the filter, right? A 3x3 filter, and then let's say you have like a image here, right? So basically you have this filter, and then you slide this filter throughout the image to get the results, right? And each result is, you have like for this pixel value, you do a summation of all the weights of the feature, this filter values to the values of the image pixel, right? So okay, so you apply this, so you can kind of see that in relation to the whole size of the image, it's really small, right? This filter, right? And then when you apply max pooling operation, you have the size of the image. So so basically now we are getting like the filter corresponds to a higher, not percentage of the image. It's not. The idea here is that it's able to get more information, right? So here we have only some pixels, neighboring pixels, but here, since you apply the downsample with max pooling, like this is kind of equivalent of this filter being doubled as well, right? Because this filter is larger because you're able to get more context of the image. So, like I said here in the example, is like proportionally, like it's able to get more of the context of the full image, right? And then likewise, when you have like another step, like you have the size again, like, so here in this toy example, like we started, like maybe this is 1/8 of the image, is able just to see like some small context size of the pixels. And then we apply some max pooling, and then like now maybe it's 1/4 of the image. And then here at the end, like this filter is more than half of the image, right? So you're able to really get like really coarse level stuff, right? So I think this, and also since we are reducing via max pooling, we are kind of also doing some compression of the information, right? So we are compressing, and max pooling, we are just getting the maximum output of this 2x2 filter that we pass through the image to have it. So we also getting only what really activated the neural network, right? So I think basically that's the idea. So here we are applying this to generate context-rich information, but we are also doing this concatenation with previous feature maps. So as we are able to get the localization where they happen, right? So does anyone have any questions here? Something was not very clear. Okay. Okay. So basically, and I think like the last aspect of the paper, not the paper, but the architecture. First, I think I already talked about that you only have convolutional layers, right? Apart from the max pooling of convolutional layers. So you have an image as input and image as output. But I think the last observation that I have about the paper is that like they say here like, oh, it's U-net because it's U-shaped, right? But I guess someone could argue that, oh, if you have like, I don't know, have like some image here, and then you apply, like this downsampling operation, and then you have like a smaller filters, and then you apply some, some smaller operations, and then you do the upsampling, and then you do the upsampling again. Oh my God, it's not that good drawing. Okay, and then you do like, oh, and now we have these skip connections here. So now it basically is the same network, but it's not U-shaped, right? So why U-net? Because this is kind of arbitrary, right? And when I first read the paper, I thought that, right? Because they are drawing this because they want, right? Because no one it's just how you're shaping the architecture, right? So it's like a graph, right? You represent a graph the way you can represent a graph in numerous ways, right? But I think the part that I think it really makes sense is that like if you go left to right, you have downsampling, right? So you're going down here if you have like here, and then here you're going up, right? So I think it kind of makes sense, right? So you start with the huge image, and then you have a size of the image goes down, down, and down, the feature maps actually, and then the feature mapper is going up, up, up. So here in the input, you have a huge image, and then its parts get smaller, smaller, then gets higher and higher, and then you have an image that's kind of similar sized. So I think that's why it's U-net, right? So I think the first time I read the paper, I didn't agree with the authors, but now I agree, right? Okay, but I think basically that's it about the architecture. But just me have a quick look here. Yeah, I think that's it about the architecture. So guys, if you have any questions, I will continue the paper here, but you can ask questions at the end, I guess. Okay, so basically I talk about the architecture of the U-net. And here I think is an important aspect that I also going to talk in the other paper is that like their tasks, and also I'm going to talk here later on the paper, is that they have very little training data available. It's like 30, 20 images, so it's really, really small, especially to train a neural network, right? So they use here, it's the highlight didn't work. You guys can see the highlight, right? So like we use excessive data augmentation. So we really they applied some deformations to the image as to get more images to be trained. And here they also they say here, like, this is particularly important in biomedical segmentation, because these deformations, they are really common in tissues to happen, and they can be realistically simulated. So I think that's also very interesting to people to know about this type of problem, right? You have to know this to be able also to tackle the problem. And also another thing that they go into is that is a challenge when they want to do some cell segmentation, is that you have some touching objects are of the same class. So basically, like, let's say that you have here, let's go here, delete this. So let's say that you have an image that, okay, so have like some fat cell, right? So, and then the fat cells are touching like this, right? And okay, but then at the end of the image, if you're thinking about doing like pixel wise, like it's kind of probable that if you don't do anything important, like instead of getting like, oh, these are 3 cells, you get like, oh, this is just one big blob that is the cell, right? And this is not very good for them, right? Because it's very important, for biomedical stuff to, understand the cells, the shape of the cells, and also how many cells you have in an image, right? So oh my God, okay. So this bordering information is really important to know as well, right? So basically here they do a weighted, they propose the use of a weighted loss. So they created a weighted map. So if you do a mistake in an area that's associated with a border, you have a higher error than if you're not, like, you make a mistake in another part of the image, you're like, okay, it's just another error. Okay, so they go into the network architecture here. So I think it's already explained a bit, but basically they have like the sequence of 3x3 convolutional layers, each one with the hello function, and then they do 2x2 max pooling operation. So basically 2x2 max pooling, you are having the size of the image a teach downsampling unit. And then they go to the expensive path, which is the upsampling. So they apply a 2x2 convolutional. So it's kind of, I think it's also interesting that they apply a 2x2 convolutional layer, because also the upsampling aspect here, it's like a learnable parameter, right? So they are not just duplicating the pixels and say like, oh, duplicating stuff and say, oh yeah, now the image is half double the resolution, right? So they do something that will try to do some intelligent upsampling in some way, right? Of course, not perfect, but it's something. And then here, the part here, they do a concatenation of the feature maps with the correspondent cropped feature maps from the contracting path. So like I said here, have all this one is a summation of this path here, but also the results that you have in this previous step. Okay. So basically here is the problem. Here is the problem that I said. This is the first problem that they talk about the cells. So basically here is the weight of the borders, right? So here we have the true image. Here we have the true labels, right? So here we have for each color, the cells are the same, but it's really to differentiate the different cells. And they also computed here a border between all the objects. And then here we have they have here the weight of the loss. So like if you make a mistake, in the cells, your mistake is level 1, right? So you don't have any extra weight associated with. But if you are a pixel that borders, between cells, you guys can see really, but it's like 10 here. The red values here is 10. So it's the making a mistake here in the border is 10 times weights 10 times more in the weight function and the loss function, then you make a mistake elsewhere. So you can kind of see as a gradient. So how they do that? Basically, they compute a weight map of the segmentations, and then they apply here a weight associated. So you have this WC basically is the weight map to balance the cross frequencies. So in this case, like what is background and what is cell in the image. And then here to compute this, this weight, they do the distance between like, the distance to the border of the nearest cell, the distance of the border of the second nearest cell, right? Because like if you're here, like, right, because if you're like just near one cell, it's okay, right? Making a mistake, it's not a big issue, right? But if you are inside between two cells, now it's costly, right? Because you're making mistakes, say like, oh, this is actually a cell. Actually, you're just merging two different cells, which shouldn't happen, right? So that's why they do that. But okay, so they do this, and then they compute this weight map to improve results. And then next step, they talk about the data augmentation. So like I said in the previous steps of the paper, they apply some operations. So they apply some shift rotation operations, and they also do some deformations on the grayscale values. So maybe they make the image slightly darker, the image is slightly brighter, maybe they change a bit of the contrast of the image, etc. So they generate a very they vary a lot of the image, right? To get the images, they also know the truth, so it's kind of simple to do that. And they say here that these deformations, they seem to be the key concept to train a segmentation network with very few annotated images. Okay, so now we are going to the experiment parts and the results. So first one is this one here, right? The segmentation of the cells. And I think it's really interesting because here, like the training data set is 30 images, like it's really small. The authors of the paper, they don't go into detail of how much they did the data augmentation, right? How much images, because at 30 images, maybe they have 100 different operations, right? So you have 100 times 30, and then you have all 300, yeah, like 100 images, right? So they don't go into detail, but it's really very few images, right? 30 images. And then they go here, and then I think here they went a bit cheeky, the authors, because here they go the table, and then they hang here, and then you see like ranking. Oh, UNet is the first one, right? So UNet is the best, but actually like ranking of the EM segmentation challenge sorted by warping error. So if you look here, like the UNet does not get the best in these other metrics, like the hand error, the pixel error is better in the warping error. So it's, I don't know, I think it's a bit, I don't know, why just to show the, I don't know, I think it's a bit misleading on their part. But I thought it was funny, right? Why they do this, right? Especially when they go here on the start of the paper, that they talk here like, oh, we earned this challenge in large margin, and then like the other one, they don't do that, and they just say, oh yeah, just in this one. And also even the error is kind of small. I don't know. I digress. But I think more interestingly, they have here the second and third challenges that they applied. So basically here we have, again, some cell segmentation task. So they have here a cell image, and then you have the results. So here, like in cyan or green or blue, it's the results of the UNet, and in yellow is the true label that was in the validation set, right? So you can kind of see that there's some imperfections, but it's really, really close, right? So they intersect pretty well. And these other challenges, the same thing, right? So you have really low contrast image, right? It's kind of even hard for a human to do that, right? But here you can see in yellow the true label, and then here in color you can see the results of the UNet. So you can see that maybe it's not perfect, all the cells, but it's really, 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 really good, right? The results, right? And I think it's more important is that like the UNet here, like they have the intersection over UNet, so the intersection between the true label and the network results. Here, like it was the second best was 83%, and then it goes to 92. and then the other challenge was 46 and go to 77%. So it's really a huge increase, right? The usage of these architectures. So I think it's really, really interesting results. And again, in this other chart, I have 35 images, and the other one has just 20 images. So it's really, I guess that's a lot of data augmentation that they do to be able to train a network. That's really, that, I mean, now it's not, maybe it's not considered as deep, with all GPT, LLMs and stuff like that, but it's kind of deep, right? Especially that you have only connected convolutional layers, right? So you have 1, 2, 3, 1, 2, 3, 1, 2, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 3 by 3 convolutional. So it's really a lot of layers. It's kind of deep network. Okay, so basically that's it for the paper. They go into the conclusion. They say, oh yeah, the UNET they got some very good results, but then they went kind of prophetic here in the last phrase of the paper that they say here, like, we are sure that the UNET architecture can be applied easily to many more tasks. So like I said here, I showed you some examples of satellite imagery and stuff. But then when you search for Google in UNET, like, you'll be able to see that is a paper, it was cited by 64,000 papers. So it's really one of the most cited papers, I guess, from recent times. So it was really, really important paper. And I think, like, I'm going to show later, right, the paper on document images, but just to show that I also put it here on the document of the session. Some other applications, right? So here we have this one that applied a variation of the UNET to small object detection. So here you can see, like, some look at that, really small objects in the image, and it's able to get, like, get some good results also compared to other techniques. But I just talking about, like, how UNET is used not only for biomedical imagery. And this one I think is also interesting, is also for, I think it's detection, is satellite imagery, but detection of banana plantations. Yeah, banana plantations. And basically you can see here, like, in blue is the true label, and the UNET is in yellow here. So you can kind of see it's near perfect. And I think it's more important, it's funny here in this paper that they say here, I note in figure 646, that the UNET classification identify a new plantation that was missed in the validation set. So here, like, you see that the UNET was able to find this plantation, and then the guys missed that. So it's kind of funny, right? Because, like, technically the network make a mistake, but then the guys seeing that say, like, oh, actually we missed to label this thing, right? Because this is actual plantation, right? So, and also I think it shows, like, how powerful this technique is, right? This like, getting the location context, and also the feature rich context, right? So I think that's it for the UNET for me. So let me just write down. So do you guys have any questions? Some quick questions before I move to the other paper, or comments? Okay. Okay, guys, so now we kind of have time. Okay, that's good. So I'm going to talk about this other paper. That's really short paper. The usage of UNET for pre-processing document images. This was a paper that was published on the CIBGRAPI conference, which is the Graphics, Patterns, and Images conference. Just to give a context why this paper is so short, right? It's just 4 pages. It's because it was not approved as a full paper, the main track, but it was approved in the track of industry application papers, right? So here you can see here, like, the paper. So maybe it's something that related to that, why they did this very short paper, right? Just to show the results and the application that they are using, right? Because the guys are from also Itaú, right? So it's application in the industry of, image processing techniques. Okay, so I'm going to, so basically they go here in the paper about, like, how to do document analysis or extracting information from documents. So they say here that it's very common to deal with artifacts that may cause problems when you want to do document analysis. You have stamps, you have noise, you have strange backgrounds, or you have a photo of someone that really is a bit not perfect aligned, right? So it's a bit crooked in a way. So that's also some noise that's added. So in order here, they train two. They have two problems here, and they train two units to solve each of the problems. And the thing that I think is more interesting about this application is here, right? One of the main advantages presented is that the models are trained on artificial data. So avoiding the wearisome task of data labeling, right? Because you know, you're getting some text documents. So it's kind of interesting this, right? Because you are doing the artificial data, so we are generating ourselves the text, the real text. So we don't need a human to write down what the text is about, right? So, and also you can try to do some simulations of the perturbations to see if it's similar to the real world scenario, right? That we receive, I don't know, documents that we ask for people, right? Okay, so then I go and hear the paper. So basically they talk here about when a document is scanned, which I think is really the best case scenario, right? Because like when you ask the guys to send some documents, they're more likely to send photos, which have more noise, I suppose. But even scanners, they have some associated noise with it, right? Because the scanner may do some techniques to save computational power or save memory. So they do some thresholding, some quantization, some compression of the data, or that we can do some image resolution, and also you lose the quality, right? So it makes a lower quality of the image. And then they ask here also that there's some really hard stuff like detecting like handwritten text. We have some lines. We have some stamps in the image. Like I said, it may be crooked and stuff like that. And then they go here that one of the main applications in document analysis is the OCR, optical character recognition, that basically consists in you have an image of a text and you converting that to a string. So we are able to extract the information. If you have a string, you can run, you know, all the stuff that we want with that, right? So you get, oh, what's the name? You can use GPT and stuff like that. Okay, so, but they go here like, oh, most of the solutions from a well-behaved scenario, which may not be true for most real case applications, and therefore it may be an issue, right? You have these noisy images. And thus, they talk here about pre- and post-processing steps really need to be considered to improve the results of the operations, right? So, and also they talk here, the major issue using OCR techniques is the high variability in page layout and design. So if you're asking, for instance, like a document of a client, he may send like, I don't know, their contract, they may send like their license, their passport, I don't know, some varied documents, and we need to extract the data from that, but it's not all the same, right? Some may be in a very, you know, a A4 paper that is vertical, some may send horizontal, some may send X and Y and Z ways, right? So it's really hard because it's really not constrained, right? It depends on the data that we have. Here again, they talk a bit again about that's a very complex problem because you have a lot of noise. So you have some stamps that may overlap the texts or some other drawing that may overlap. So this is really hard. So motivated by these gaps, they propose using UNet in two scenarios. So the first scenario is the segmentation of image-made text to improve OCR. So basically, it's here. So basically, we have an image that they created with some noise and some stamps here, and they want to just have the text of the image and then use this text to feed the OCR. And the second one is the extraction of handwritten text to help applications such as signature verification. So basically here, like you have like a contract, a pseudo contract, and then you have here a signature of someone, right? And then like, let's say that we want to verify like if a contract, like the guy that signed the contract is the same guy that we have the information. I don't know. How could we automatize this operation, right? It's not trivial, right? Because we may have the signature, but we don't know where the signature is, right? So you would require a human to say like, oh, this is the sign of the guy, and then you have an image of that to compare, right? And maybe in the future we could have a neural network that could, like compare the signatures. But to compare the signatures, first we also need to know where is the signature, right? So basically why this is important, right? So you have here a lot of noise, some text here, and in the end you have only this the text written, right? And basically here we can just apply some very easy like bounding box operation on the what we have here on the text. And then with that we can say like, oh, actually it's here the signature, and then we can feed this to a network that, I don't know, says if the signature is real or a faked one. I don't know. So, I mean, they don't go into detail, but this is an example of how it could be used in a downstream task. Someone asked something. Do you think it would be good enough to have an ID with the signature and then assign a document to compare? I think it depends on the use case. I think it depends on the use case, right? Because we also wouldn't have much data, right, to do that. But I think like you have some data from previous documents, it would be a good indication. Okay, so let me continue here with the paper. So have here, like they go again with the technical background. So like I already presented the UNet architecture they used. And here I think it's really interesting that a great advantage presented by this model is that it's fully convolutional and thus can operate in any image scenario, and therefore is very suitable for this work scenario. And I think this is really interesting, right? Because like I said, you have like image like a contract, some images that are vertical, some images that are horizontal oriented, some images that are big, some images that are high resolution, some images that are really take like a photo by a potato, so have a really low resolution. So doing this technique, fully convolutional neural network, we are not bound to like, oh, we have to convert this image to a fixed size every time and then feed that to get the results. We can feed the image. We have to do some operation like to make sure that it's even the number of the image, you have even number of pixels to do the downsampling, upsampling, they convert. But apart from that, we can apply to a different array of images, right, of different sizes and orientations. And then here they go about like one of the main challenges of the document analysis. So like they say here, like up until recently, such task is done manually by humans, which can be extremely time consuming. So have like an image of a document and say like, oh, human, type this. So you go like to Amazon and the other other services that you for data labeling, right? And then like you have like, oh, right now this image, the document, but it's also like very time consuming, so it's very expensive, but also can be you also have the noise of the people that is writing, right? Because he may mistype something, the image is too large, he may mistype, or he didn't read correctly, right? So it's really a problem, right, to do this. And then here they go, the idea that he say here, like this issue can be bypassed by generating synthetic images as done in this other work. So you generate some synthetic images here, like, so have like, oh, these are images that are synthetic. And one interesting thing is that since we are generating the images, we know the ground truth text, right? So it's really easier to evaluate, like, oh, the guy really got all the text correctly, he mistakes some words or some characters, but we have the ground truth, so it's really easy to do this comparison. And another thing that's really interesting is that you can apply any variability to the data. So you can make like you can have levels, right? So have a document, a contract document, and then you apply just a few noise. Oh, it's easier. Then you apply some warping and rotation, and you apply more noise. So you make as hard to try to generalize that, right? So you can see like where, for instance, the OCR breaks or not, right? So basically here they created their own artificial data set to train the two UNets, one for retrieving handwritten text, and the second to maintain only the machine written text that is used to feed the OCR. And also they use here the signatures. They use this CIDAR database. They have like 1,000 signatures, and then they apply some operations, and I think that's fine, right? And then also they use these signatures to add at random spots in the image. And another artifact that they think is important to verify is stamps. So like here, right, you have stamps here, and then like the stamps are over the image, right? So it would be good that we could retrieve the correct textual information, even with have these stamps, right? Which would be very hard even for a human to read, right? So the idea is that we have the true label, so you try to feed the network to learn like, oh, even this stamp, they are able to correctly identify the characters that are under this stamp. Yeah, so basically here, like they want to create really real life documents, so they create conditions, so they like add random lines, some grids like tables, and then like the signatures. And also here they also go into like they don't just apply the stamp, that are two stamps that they did, but they also do some operations, so have like the morphological operation, so a dilation, erosion, and also some noise applied to it. Okay. So, okay, we have all these operations of noise adding that we have. So they have like a noisy image and a label image, right? Because you have the label image will be only the text. So only the target text is showcased here with the background set to 0. So here you have the example here, right? So have like, oh, this in one, in white is what we want the text, and the background is everything else, right? Including the steps. Here they go to talk a bit about the OCR. So the OCR they use is the Tesseract, which is the most common used OCR engine. And they say here like the OCR is treated like a black box because retraining the model would be like you'd require a great deal of labeled data, right? Because like you have to retrain an OCR, so you have like thousands and thousands of images and thousands of labeled images. So they consider that it's more it makes more sense for them to consider like the OCR part like a black box. So they like they're trying to improve the image before you feed to the OCR. So and then you see the results of the OCR. Okay, so basically here they talk a bit about the repository where they say like how to evaluate the results of the OCR. And I think it's kind of obvious, but I think it's also very important, like think about document analysis, is that at least for this package, like it's important to mention that the ground truth text is needed to compute the number of mistakes, which is kind of obvious, right? But I also think it's interesting, right? Because if you are not, if you are applying OCR to documents that we don't know, how can we evaluate the quality of the OCR, right? How can we evaluate the text extracted is good or not too noisy to be used, right? Oh, the name of the guy have some mistakes, or the whole structure of the text makes mistakes, right? So I think this is an interesting problem. Of course, it's not really what they're doing here, right? But I think it's something that I think we should consider when working with OCRs. Okay, so basically here, and getting already the end of the paper, so basically here, like the metrics that they use, so they have the SIR, character error rate, which basically is the number of errors of the characters of the OCR, and they have the WER, like the word error rate, which is basically the same thing, but considering the characters, the words, right? So I guess a word here is considered some text that is between spaces, right? Okay, and then here, like again, they talk here, like as we aim to test this OCR in document analysis for real-world documents, so they try to generate real-world images that would resemble really real-world documents. So here they talk here about how they used Wikipedia to get natural language text. So they use Wikipedia to get some text. And here, like they talk here about how they added noise to the image to account several image complexity scenarios. So like I said before, you can have like some small noise, and then you can add more noise to make the problem more hard. All right. Here in the end, they talk here, as a result, we had 1,000 noisy images where Tesseract OCR was applied before and after our model. So then we can compare the results before and post the processing operation. So here is the example here that they have here in the image for, so I think it's easier for you guys to see. So here, like, os tipos de bactéria que causam meningite bacteriana. So we have some text from Wikipedia. And then you have like this black and pepper noise here, that is black spots here. They add some signatures, so have some in the end of the image, and also some signatures over the text, and also some stamps over the image. So you have like a really, try to replicate like what would be hard scenarios, right? Okay, and also here they go for the handwritten text recognition, where basically they just do a qualitative image evaluation, say like, oh, it did distract, it did mask the written text, or it didn't. Okay, so finally we got into the results section. So basically here we have the word, both the word recognition and character recognition performance. And then you have in orange is the original, so the noisy image before the OCR. And then in green you have the noisy image after the UNet, then you feed to the OCR. So you can see here that they compute the average ratio, like of how good it is. You can see like a recognition performance, right? So you can see that is an improvement, right? So here like 5% and here 14%. So here, especially character recognition, it improved a lot the results. But I think one interesting aspect, I think, is that you can kind of see that, okay, in both cases, it improved results, the UNet, but also you can see that in some documents that it performed really well, the noisy image. So maybe it's a case of low noise or image without any noise. You can see that you have the document before it performed really well, but then it kind of did it, right? Because here are the same documents, right? So the document maybe achieved like a 90% performance, and now it's 85, I don't know. So I think it's also interesting to see that maybe if you have one pipeline of processing documents, is not ideal, right? Because maybe you have a pipeline to get harder stuff, and then maybe you don't need a pipeline at all for cases that are kind of easy, right? So it's something that, but how we assess that, right? So I think it's an interesting aspect of this paper is this, right? It improved results, but not necessarily really improved results. So in the same case here, right? Here for character recognition, the gap is huge, 14% increase. But here you can also see that the best documents here are still only orange, right? So I think this is really interesting and maybe unexpected. Okay, so finally here we go to the conclusion. So they say here like one of the main advantages of our approach is the generation of artificial training data. So we don't need to get like other people to assess that. And here also they go to the part, the signature part, right? So here you have the image, you have like contract here. So you have some signatures here, and then they feed this to the UNet, and the results are kind of good, right? You can kind of see it only got this stuff. You may see that have some imperfections here and there, but it's really good, right? So you can kind of use this, like, and then you apply some image segmentation to get like extract the signatures and then later compare, or the initials, right? So it's really, really interesting results. Okay, so in the conclusions, they say that our initial results, the pre-processing technique is very suitable for your scenarios with large image degradation. And then they say here, like in regards to detection of handwritten text, is also kind of good, right? Of course, they're doing only extraction, right? They're not feeding this to the OCR because they're more focused on signature detection. And I think that's it, guys. So does anyone have any questions or comments?